Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
Interstellar space forms the outermost region of this inquiry, a vast and diffuse environment where matter drifts between stars without attachment to any single system. In this region, distances are measured not by proximity but by absence. Gravity weakens, light thins, and objects travel for long intervals without interaction. It is from this environment that 3I Atlas arrives. Its origin is not traced to a specific star, but its motion carries the unmistakable signature of formation beyond the solar system. This signature is established through velocity and direction alone. The object approaches with a speed relative to the Sun that exceeds what bound orbits can sustain. Its path does not loop or return. It enters, passes through, and continues outward, consistent with material shaped elsewhere, and only briefly influenced by local forces. The recognition of such arrivals depends on an infrastructure designed to notice faint motion against a stable background. Wide-field surveys scan large portions of the sky, repeatedly comparing images separated by time. Stars remain fixed relative to one another while nearby objects shift slightly. Most of these moving points are familiar residents of the solar system asteroids and comets, following predictable paths. A smaller number exhibit unusual speeds or directions. Among these are very few display trajectories that cannot be reconciled with long-term solar system residents. These are identified as interstellar visitors. 3I Atlas is detected through this process. Its initial appearance does not differ visually from other small bodies. It presents as a faint point of light reflecting sunlight weakly. Only through repeated measurements does its distinct nature emerge. Each position is recorded relative to background stars whose locations are known with high precision. Over time, the object's motion reveals a trajectory that does not curve into a closed orbit. Instead, it follows a hyperbolic path, one that approaches from interstellar space and departs back into it. The concept of a predicted trajectory arises immediately. Prediction in this context does not imply certainty but expectation based on known forces. Gravity from the Sun and planets dominates motion within the solar system. Given an initial position and velocity, classical mechanics provides a clear forecast of future locations. These forecasts improve as additional data points are added. Early predictions are provisional, bounded by uncertainty. Later predictions narrow as measurement error decreases. At the outermost stage before any deviation is considered 3. I-Atlas is treated no differently than other incoming objects. Its trajectory is calculated under the assumption that gravity alone governs its motion. This assumption is not naive. It reflects the overwhelming success of gravitational models in describing solar system dynamics. Deviations are rare and usually attributable to well-understood processes such as outgassing from icy surfaces. At this stage, no such processes are invoked. The object is distant, cold, and faint. There is no evidence yet of activity. Interstellar origin adds complexity without drama. Objects formed around other stars are expected to differ in detail, but not in principle. They are shaped by similar physics, acting under different conditions. Their materials may vary in composition or structure, but they obey the same laws of motion. This expectation frames the initial approach. The object is not treated as exotic. It is treated as unfamiliar. As observations accumulate, the predicted trajectory is refined. Each new measurement adjusts the model, slightly reducing uncertainty. The object's future positions are projected forward in time, allowing telescopes to follow it efficiently. This predictive loop is essential. Without it, faint objects would be lost quickly against the moving sky. Prediction here is a practical tool, not a claim about underlying cause. The phrase "no longer on its predicted trajectory" gains meaning only against this background. Prediction is always conditional. It rests on assumptions about forces and measurement accuracy. When observations diverge from expectation beyond established error bounds, the divergence does not imply error immediately. It signals the need to reassess assumptions. At the outermost region, this reassessment has not yet begun. The framework remains intact. Gravity dominates. The object behaves as anticipated within uncertainty. The environment through which 3i Atlas travels is sparse. Collisions are exceedingly unlikely. Radiation from stars exerts a gentle pressure usually negligible for compact bodies. Magnetic fields are weak and diffuse. These conditions support the initial reliance on gravitational prediction. There is nothing in the surrounding medium that suggests strong perturbation. Interstellar space also imposes time. The object has travelled for long intervals before detection, possibly millions of years. During that time, its path has been shaped by cumulative gravitational influences from stars it passed near, as well as by the overall gravitational field of the galaxy. By the time it reaches the solar system, those influences are encoded in its velocity vector. They are not active forces now. They are history. This distinction between past shaping and present motion matters. Prediction concerns present and future motion under current forces. History informs initial conditions but does not act directly. Thus, when 3i Atlas enters the predictive domain of solar system models, it is treated as a new initial value problem regardless of its long prior journey. The outer region concludes with this stable framework in place. An interstellar object is identified. Its motion is measured. A predicted trajectory is established under standard assumptions. Nothing yet challenges expectation. The system of observation operates smoothly, quietly, without urgency. Only later, as the object moves inward and data accumulates, does the question of deviation arise. For now, the outermost layer holds steady, providing a calm and reliable foundation for everything that follows. The discovery phase unfolds close to the boundary between routine survey work and focused attention. 3i Atlas first appears as a faint moving point detected by automated systems designed to notice change rather than meaning. These systems compare images taken minutes to hours apart, flagging sources that shift position against a fixed stellar background. At this stage, the object carries no identity. It is a candidate assigned a provisional designation and queued for follow-up like countless others. Its brightness is low, its motion modest, and its appearance unremarkable. Confirmation requires repetition. Additional images are obtained sometimes from the same facility, sometimes from others responding to automated alerts. Each observation records a time, a position on the sky, and an uncertainty envelope. These measurements are combined to produce a short observational arc, a brief segment of motion that allows an initial estimate of the orbit. This estimate is rough. It is sufficient only to predict where the object will be hours or days ahead, enabling continued tracking. The early orbit solution relies on minimal assumptions. The Sun is treated as the dominant mass. Planetary perturbations are included if relevant, but at this distance their influence is small. The object's path is fit using standard techniques that balance measurement error against model simplicity. Residuals, the differences between observed and predicted positions, are examined to ensure they fall within expected bounds. At this point they do. As more data points accumulate, the arc lengthens. The object's speed relative to the Sun becomes clearer. This speed is compared against escape velocity at the same distance. When it exceeds that threshold by a clear margin, the possibility of a bound orbit is excluded. The trajectory is identified as hyperbolic. This classification does not imply acceleration or deviation. It describes geometry. The path curves once and does not return. The designation 3I Atlas follows established convention. The prefix marks it as the third known interstellar object detected passing through the solar system. The remainder reflects the survey responsible for its identification. This naming is administrative. It confers no additional status. It simply allows consistent reference across databases and publications. Initial predictions are generated immediately after classification. These predictions specify the object's future positions on the sky, its changing distance from the Sun, and its expected brightness as geometry evolves. Telescopes rely on these predictions to schedule observations. Even small errors can cause the object to be lost, so predictions are updated frequently as new data arrives. This iterative process refines the orbit steadily. During this period, the phrase predicted trajectory refers to a living model. It is recalculated daily, sometimes hourly. Each revision incorporates the latest measurements, reducing uncertainty. The predicted path narrows from a broad corridor to a thin line. Confidence increases not because the model becomes complex, but because it remains stable as data grows. The object's early motion aligns well with gravitational expectation. There is no visible coma, no tail, no sign of mass loss. Its brightness varies only with distance and viewing angle. Photometric measurements suggest a small, dark body reflecting a modest fraction of incident sunlight. These characteristics are consistent with many asteroids and inactive cometary nuclei. Nothing at this stage requires additional forces. The initial orbit also establishes timing. The moment of closest approach to the Sun is estimated. So is the closest approach to Earth, if any. These estimates guide observational strategy. If the object will brighten significantly, resources may be allocated accordingly. If it will remain faint, observations are prioritized while feasible. In either case, the orbit prediction serves planning rather than interpretation. Uncertainty remains explicit. Error ellipses accompany every predicted position. These ellipses shrink as observations accumulate. The mathematics underlying them is well understood. It accounts for measurement, noise, timing, precision, and systematic offsets. When residuals fall within these envelopes, confidence in the model increases. For 3I Atlas they do. At this stage, the concept of being no longer on its predicted trajectory has not yet emerged. The prediction and the observation remain aligned. Small discrepancies appear and disappear as expected within noise. No pattern suggests persistent deviation. Analysts note nothing unusual beyond the object's interstellar origin. The discipline here is restraint. Early data is tempting to overinterpret, especially for rare objects. But institutional memory favors patience. Past cases have shown that early anomalies often vanish with additional data. This awareness shapes behavior. Claims are avoided. Language remains conditional. The orbit is described as preliminary subject to refinement. The process also involves cross-validation. Independent teams compute their own solutions using the same data. These solutions are compared. Agreement builds confidence that no computational error dominates. Minor differences are traced to methodological choices, not to underlying disagreement. Convergence occurs naturally. As the initial orbit stabilizes, it is archived and disseminated. Databases update publicly. Amateur astronomers gain access to ephemerids, sometimes contributing additional observations. These contributions are vetted and, if reliable, incorporated. The object's track becomes a collective construct built from many eyes and instruments. The predicted trajectory at this stage is still gravitational in nature. It assumes that the only significant forces acting are those of known masses. This assumption is not explicitly stated each time. It is implicit in the model's form. It reflects what has worked consistently across decades of observation. The early success of this approach reinforces confidence. The object appears exactly where expected. Each night's observations match the forecast within margins. This consistency allows attention to remain procedural. The system works as intended. This section closes with the predicted trajectory firmly established in its initial form. It is a product of careful measurement, conservative modelling, and iterative refinement. It is not a claim about permanence, it is a snapshot of understanding at a particular moment built to guide observation rather than to define truth. Only later, as conditions change and data accumulates further, does the question of deviation become meaningful. For now, the orbit holds quiet and precise, carrying the object inward along a path that appears fully accounted for. The inward progression now enters the region of reference frames and relative motion, where trajectories acquire meaning only through carefully defined perspectives. Motion in space is never absolute. It is always described with respect to something else, and the choice of that reference shapes interpretation. For 3i Atlas, several frames are used simultaneously, each serving a specific purpose, each remaining mathematically consistent with the others. The most common frame is heliocentric. In this view, the Sun is treated as the central point, and the object's position and velocity are measured relative to it. This frame is practical because the Sun dominates the gravitational field of the inner solar system. Orbital elements such as perihelion distance, inclination, and eccentricity are defined naturally here. When early predictions are made, they are almost always heliocentric, because this simplifies both calculation and communication. A second frame is barycentric, centered on the combined mass center of the solar system. This frame accounts for the fact that the Sun itself moves slightly in response to the gravitational pull of planets, especially the largest ones. For most purposes, the difference between heliocentric and barycentric descriptions is small, but for high-precision work it matters. Interstellar objects with their high velocities and brief encounters can reveal these small differences clearly. Thus, barycentric elements are often used when assessing origin and long-term motion. A third frame is geocentric, centered on Earth. This frame is used primarily for observation planning. Telescopes fixed to Earth's surface need to know where to point relative to Earth's rotation and orbit. Predicted sky positions are generated in this frame, even though underlying calculations may be heliocentric or barycentric. Transformations between frames are routine handled by well-tested software that incorporates Earth's motion, rotation, and orientation. Understanding predicted trajectories requires recognizing that a path described in one frame can appear different in another, without implying physical change. A straight line in one reference can curve in another. An acceleration measured relative to Earth may vanish when expressed relative to the Sun. Analysts remain aware of this, checking consistency across frames before interpreting residuals. For 3i Atlas, early analyses compare heliocentric and barycentric velocities to confirm interstellar origin. In the barycentric frame, the object's velocity far from the Sun remains significantly above zero, indicating it is not bound to the solar system. This confirmation is robust. It does not depend on subtle corrections or assumptions. It establishes that any predicted trajectory must connect smoothly to an incoming asymptote defined in this frame. The predicted path through the solar system is then propagated forward in time. This propagation uses numerical integration, calculating how gravitational forces change velocity incrementally as the object moves. The equations are straightforward. Force depends on mass and distance. Acceleration follows directly. Time steps are chosen small enough to maintain accuracy. The resulting trajectory is smooth and continuous. Residuals are examined in each frame. A residual is the difference between where the object is observed and where the model predicts it should be. Residuals can arise from measurement error from unmodelled forces or from frame transformation inaccuracies. At this stage, residuals for 3i Atlas are small and randomly distributed. They do not show systematic trends when plotted over time. The language of being no longer on its predicted trajectory implies a divergence that persists across frames. Such divergence must be invariant. If a discrepancy appears only in one reference frame, it is likely an artifact. True physical deviation will manifest regardless of perspective, though its expression may differ numerically. This awareness guides analysis. Before any claim of deviation is considered, analysts ensure that transformations are correct. Star catalogues are checked. Timing standards are verified. Relativistic corrections, small but measurable at high precision, are applied consistently. These steps are routine but essential. They ensure that what remains cannot be explained away by coordinate choice. In this region, attention also turns to how uncertainty propagates. Uncertainty in initial position and velocity expands over time. Predicted positions further in the future carry larger error envelopes. Thus, an object appearing outside a narrow early prediction may still fall within a broader uncertainty corridor. Analysts compare observed positions not to a single line but to a volume of possibility. For 3i Atlas, the early uncertainty corridors shrink steadily as observations accumulate. This shrinkage is expected. It reflects improved knowledge of initial conditions. As a result, later deviations become more meaningful. A discrepancy that once would have been dismissed as noise now carries weight because the corridor has narrowed. The distinction between prediction error and physical deviation becomes sharper. Prediction error diminishes with data. Physical deviation, if present, does not. It accumulates. It introduces a bias that grows systematically with time. Analysts look for this pattern, comparing residuals across frames and epochs. At this stage of the inward journey, that pattern has not yet emerged clearly. The reference frames remain aligned. Transformations behave as expected. Residuals show no consistent drift. The predicted trajectory remains valid within its refined uncertainty bounds. The importance of this stage lies in preparation rather than conclusion. By establishing robust reference frameworks and verifying their consistency, analysts ensure that later claims rest on solid ground. When deviation is eventually discussed, it will not be attributed to perspective or coordinate choice. It will be recognized as a property of the object's motion itself. Thus, Section 3 closes with a stable geometric foundation. Motion is defined carefully. Frames are aligned. Prediction remains a faithful description of expectation. The object continues inward along its calculated path, while the analytical framework stands ready to detect change without confusion. The inward progression now reaches the region where gravitational expectation is defined explicitly. Here, the predicted trajectory takes its most formal shape, expressed as motion governed solely by the gravitational influence of known masses. This region is foundational. It establishes the baseline against which all later deviations are measured. Without this baseline, there is no reference for change. Gravity in the solar system is well characterized. The Sun accounts for the vast majority of mass and thus for the dominant force acting on passing bodies. The planets contribute secondary influences that are predictable and precisely measured. Their masses, positions, and motions are known with high accuracy, refined continuously through spacecraft tracking and long-term observation. When an object enters the solar system, its motion under these forces can be calculated with confidence. For 3I Atlas, the gravitational model begins with its incoming velocity vector as measured far from the Sun. This vector defines the asymptotic approach, the direction, and speed the object would maintain in the absence of solar system influence. As it moves inward, the Sun's gravity bends this path smoothly. The curvature increases as distance decreases. The object accelerates toward the Sun, reaches a point of closest approach, and then decelerates as it climbs back out of the gravitational well. This motion is described mathematically by classical mechanics. The equations involved are centuries old and remain valid for this regime. They require no modification for objects of this size and speed. Relativistic effects are negligible at these velocities and distances, though they are included as minor corrections in high-precision integrations. The resulting trajectory is continuous, deterministic, and reversible in time. In this gravitational-only model, nothing unexpected occurs. The object's speed increases exactly as predicted. Its direction changes smoothly. There are no abrupt turns, no irregular accelerations, no unexplained pauses. The predicted positions form a clean curve through space 1 that can be extrapolated forward and backward with equal reliability. The predicted trajectory is not a single line, but a solution family. Each solution corresponds to slightly different initial conditions within the uncertainty bounds of measurement. Together they form a narrow tube of possible paths. As observations accumulate, this tube narrows. Confidence increases not because uncertainty vanishes, but because it becomes constrained. Planetary perturbations are included carefully. If the object passes near a planet even at great distance, the planet's gravity can alter its path slightly. These effects are calculated precisely. For 3I Atlas, no close planetary encounters occur. The object remains far from the major planets, and their contributions remain small and smooth. There are no sudden gravitational impulses. The predicted brightness evolution is also derived from the gravitational path. As distance to the Sun decreases, illumination increases. As distance to Earth changes, apparent brightness adjusts accordingly. These changes follow inverse square relationships. They are gradual and predictable. Photometric observations align with these expectations, early on reinforcing confidence in the gravitational model. At this stage, the phrase "no longer on its predicted trajectory" has no application. The predicted path and the observed motion coincide within uncertainty. The object appears exactly where gravity says it should be. Each new data point reinforces the model rather than challenging it. This alignment is important psychologically as well as scientifically. It establishes trust in the baseline. Analysts gain confidence that the system is functioning correctly, that measurements are reliable, and that models are appropriate. This trust ensures that later deviations, if they appear, will be taken seriously rather than dismissed reflexively. The gravitational model also serves as a filter. It allows analysts to subtract expected motion from observed motion, leaving residuals that can be examined independently. These residuals are initially small and structureless. They do not trend with time. They do not correlate with distance or orientation. They behave like noise. Attention remains procedural. Orbit updates are published. Observations continue. No special language is used. The object is described as following a hyperbolic trajectory consistent with gravitational prediction. Reports remain concise and conservative. It is within this calm that the significance of later change will emerge. If an object deviates from a gravitational path, the deviation is meaningful only because the gravitational path is so well understood. This understanding has been earned through countless confirmations across centuries of observation. It is not speculative, it is empirical. The inward movement through this region completes the establishment of expectation. Gravity defines what should happen if nothing else intervenes. It provides the reference against which everything else is measured. The predicted trajectory is not a guess. It is a calculation grounded in known mass and motion. As Atlas continues inward along this path, the baseline holds steady. Nothing yet suggests that the object will depart from it. The gravitational framework remains intact, precise, and sufficient. Only as the object moves closer and observations grow more detailed does the possibility of subtle divergence enter consideration. For now, the predicted trajectory remains exactly that, a faithful description of motion, under gravity alone, unchallenged and complete. The inward movement now reaches the region where expectation and observation begin to separate by a margin that invites attention. This separation does not announce itself abruptly. It emerges gradually as a pattern forming quietly within residuals that no longer behave as random noise. At first, the differences are small, comparable in size to measurement uncertainty. They do not trigger alarm. They are noted, logged, and watched. Residuals are plotted over time. Early points scatter evenly around zero. Later points begin to favour one side. The displacement is subtle, measured in fractions of arcseconds, but it is persistent. When the object is observed on successive nights, its position consistently falls slightly ahead of or behind the predicted location derived from the gravitational model. The direction of this offset remains stable across observations. At this stage, analysts respond cautiously. The first assumption is not that the object has changed behaviour, but that the model or the data may be incomplete. Instrument calibration is reviewed. Timing accuracy is verified. Star catalogues are checked for systematic offsets. Independent observations from different facilities are compared. The offset persists across instruments and observers. The predicted trajectory is updated using the new data. The fitting algorithm adjusts initial conditions to minimize residuals. If the discrepancy were due solely to early uncertainty, the updated model would absorb it. Instead, while the fit improves locally, residuals reappear as additional data is added. The same directional bias returns. This repetition distinguishes the effect from noise. The phrase no longer on its predicted trajectory begins to acquire operational meaning. It does not mean the object has departed dramatically from expectation. It means that the original assumption, gravity alone, no longer produces a model that remains consistent as data accumulates. The prediction must be revised not because it was careless, but because its scope was limited. The magnitude of the deviation is quantified carefully. Analysts express it as a small acceleration component not accounted for by gravity. This component is tiny compared to the Sun's pull, but over time it produces a measurable shift. Its direction is examined relative to the Sun, the object's velocity, and the observer's line of sight. Patterns matter more than size. At this point, caution remains paramount. A single source of systematic error could mimic such an effect. Atmospheric refraction, unmodelled detector distortion, or catalogue biases could introduce consistent offsets. Each possibility is evaluated. None explain the observed trend adequately. The effect remains after corrections. The deviation does not appear suddenly at a particular distance. It grows gradually as the object moves inward. This behavior suggests a force that increases with proximity to the Sun, but not one that dominates. The acceleration scales weakly with distance, consistent with processes activated by solar heating or radiation rather than by gravitational encounters. Importantly, the object still follows a broadly hyperbolic path. It is not captured. It does not reverse direction. The deviation modifies the trajectory slightly but does not redefine it. This distinction prevents overinterpretation. The object is not behaving erratically. It is responding to an additional influence layered atop gravity. The predicted trajectory is now explicitly labeled gravitational only. Alternative models are introduced for comparison. These models add a small non-gravitational term to the equations of motion. The form of this term is not fixed initially. Analysts test simple parameterizations, adjusting magnitude and direction to see which best reduces residuals. This testing is exploratory, not explanatory. With the added term, fits improve significantly. Residuals shrink and lose their systematic trend. The improvement is statistical and reproducible. It does not depend on a single data subset. This outcome confirms that the deviation is real in the modeling sense. Something beyond gravity is acting. Even here, language remains restrained. The object is described as exhibiting a deviation from the purely gravitational trajectory. The cause is not specified. No claim is made about mechanism. The focus remains on description rather than explanation. The timing of this recognition is important. It occurs only after sufficient data is accumulated to rule out simpler causes. This delay is not hesitation. It is methodological discipline. By the time the phrase "no longer on its predicted trajectory" appears in internal discussion, it carries weight precisely because it was not used earlier. The inward movement through this region marks a shift in posture. The question is no longer whether the object follows gravity alone. It is how additional influences might operate within known physics. The trajectory is still predicted, but the prediction now includes new terms. The model grows slightly more complex but not unstable. Throughout this process, communication remains measured. Updates to public databases note the revised orbit solution. Uncertainties are stated clearly. The deviation is described quantitatively, not qualitatively. There is no language of surprise. There is recognition. As this section closes, the object continues inward. Its path is still smooth. Its motion is still predictable, though the prediction now acknowledges an extra influence. The predicted trajectory has changed, not because the object has acted unpredictably, but because understanding has refined. The deviation has been identified, isolated, and bounded. It stands as an observation, not a conclusion awaiting deeper examination, as the inquiry moves further inward. The inward progression now enters the region where measurement itself becomes the central subject. Here the question is not what forces might act on 3i Atlas, but whether the observed deviation can be fully accounted for by limits of observation and analysis. This region is defined by error not as failure, but as an inherent property of any attempt to describe motion across vast distances using finite instruments. Every recorded position of the object carries uncertainty. This uncertainty arises from multiple sources: atmospheric distortion for ground-based telescopes detector, resolution tracking, precision timing, accuracy, and the reference star catalogue used to anchor measurements. Each source contributes a small amount of imprecision. Combined, they form an uncertainty envelope around each data point. At large distances, this envelope is relatively wide. The object appears faint and slow-moving. Small errors in centroid determination translate into larger positional uncertainty. As the object moves closer and brightens, individual measurements improve. The envelope narrows. This narrowing is expected and is reflected explicitly in orbit solutions. The key question in this region is whether the observed deviation exceeds what these envelopes allow. Analysts examine residuals normalized by their uncertainties. If residuals cluster within one standard deviation, they are consistent with noise. If they consistently exceed that range in a coherent direction, they indicate a real effect. For 3I Atlas, the latter pattern emerges gradually and then stabilizes. Systematic error receives particular scrutiny. Unlike random noise, systematic error produces consistent bias. Analysts test for correlations between residuals and observing conditions. They examine whether offsets depend on telescope detector sky position or time of night. They compare observations made with different instruments under different conditions. The deviation persists across these variables. Timing accuracy is verified. Even small timing errors can shift predicted positions noticeably for fast-moving objects. Observatory clocks are checked against standards. Timestamps are reprocessed where necessary. Corrections do not eliminate the deviation. Star catalogues are another potential source of bias. Object positions are measured relative to background stars whose coordinates are known from large astrometric missions. If catalogue errors are present, they can introduce coherent offsets. Analysts test multiple catalogues and apply updated corrections. The trend remains. The fitting process itself is examined. Orbit determination relies on numerical methods that minimize residuals. Different fitting algorithms are applied to the same data. Solutions converge on similar results. The inferred non-gravitational term appears regardless of method, though its exact magnitude varies slightly within uncertainty. Outlier rejection is handled conservatively. No data points are removed without clear justification. When suspected outliers are excluded temporarily, the deviation does not disappear. This indicates that the effect is not driven by a few anomalous measurements. Analysts also examine whether the deviation could result from incorrect modelling of planetary masses or positions. These quantities are known with extreme precision. Adjustments within their uncertainties produce changes far smaller than observed. This avenue is closed quickly. The role of relativistic corrections is considered. While small, such corrections are standard in high-precision orbit determination. They're included consistently. Their omission or inclusion does not account for the pattern observed. Through this process, confidence grows that the deviation is not an artifact of measurement or analysis. This confidence does not come from a single test, but from convergence. Independent checks lead to the same conclusion. Error has been explored thoroughly and found insufficient. Importantly, the deviation remains small. It does not overwhelm measurement noise. It emerges only because noise has been reduced through accumulation of data. This fact reinforces the significance of patience. Without extended observation, the effect would remain hidden. The language used internally reflects this balance. Analysts speak of detection significance, signal-to-noise ratios, and confidence intervals. They avoid absolute statements. The deviation is described as statistically significant within current data, subject to revision if future observations contradict it. This region of analysis is often overlooked externally, yet it is here that most claims fail. Many apparent anomalies dissolve under careful error analysis. 3I Atlas passes this test not dramatically but convincingly. The deviation remains after error is exhausted. As the inward movement continues, the inquiry is now prepared to consider physical causes. Measurement has been interrogated and found adequate. The deviation stands as a property of the object's motion rather than of the instruments observing it. This transition is quiet but decisive. Section 6 closes with a refined confidence. The object is indeed no longer following the trajectory predicted by gravity alone, and this conclusion rests not on speculation, but on disciplined elimination of alternative explanations. The path forward leads inward toward forces and properties capable of producing the observed effect, grounded firmly on the reliability of the measurements that revealed it. With measurement error constrained and confidence established that the deviation is real, the inquiry turns inward to physical mechanisms that could plausibly alter the trajectory without invoking extraordinary assumptions. The role here is not to speculate wildly, but to enumerate known forces, evaluate their magnitude, and test their compatibility with the observed behavior. This section is defined by restraint. Each mechanism is considered not because it is exciting, but because it is necessary to rule it in or out. The most immediate candidate is outgassing. For comets, this is the dominant non-gravitational force. As volatile ices sublimate, escaping gas produces thrust. This thrust can measurably alter an object's orbit, especially for small bodies with low mass. The effect has been observed countless times in long-period comets and is routinely included in orbital models as a standard non-gravitational parameter. At first glance, 3I Atlas appears compatible with this explanation. It displays a coma. It brightens as it approaches the sun. These are classical signatures of sublimation. However, the details complicate the picture. The magnitude and direction of the deviation do not align cleanly with simple outgassing models. Outgassing thrust is strongly dependent on solar distance and illumination geometry. It typically increases smoothly as an object approaches perihelion and decreases afterward. The thrust vector is often aligned roughly anti-solar, modulated by rotation and surface heterogeneity. For 3I Atlas, the deviation does not follow this pattern precisely. Its onset appears earlier than expected, and its directional components show stability inconsistent with rapidly changing illumination. Spectroscopic observations deepen the ambiguity. While gas species are detected, their production rates are modest relative to the inferred thrust. In typical comets, measured gas output correlates reasonably with observed non-gravitational acceleration. Here the correlation is weaker. This does not rule out outgassing, but it suggests either an unusual composition or an atypical geometry. One proposed refinement involves highly collimated jets. If outgassing is concentrated in narrow regions, thrust efficiency increases. A small amount of gas, if expelled in a consistent direction, can produce a disproportionate effect. This scenario requires a stable rotational state and persistent active regions. Observations of brightness variation suggest rotation, but the inferred period and amplitude leave room for uncertainty. Another consideration is the role of supervolatile species. Substances such as carbon monoxide or nitrogen sublimate at much greater distances than water ice. An object originating in interstellar space may retain such volatiles near its surface. Early activation driven by these species could explain deviation onset at larger heliocentric distances. However, direct detection of these gases remains challenging, and current data do not definitively confirm their dominance. Radiation pressure is examined next. For very small or low-density objects, solar radiation can exert measurable force. This was a prominent hypothesis for previous interstellar objects. Radiation pressure scales with surface area rather than mass, making it significant for objects with high area-to-mass ratios. To produce the observed deviation, 3i Atlas would need to be unusually thin or porous. Photometric data constrain size and reflectivity, while uncertainties remain. The inferred dimensions suggest a body larger and denser than would be required for radiation pressure to dominate. Additionally, the deviation's dependence on distance does not match the inverse square scaling expected for pure radiation pressure. This mechanism is therefore considered secondary at most. Thermal effects such as the Yarkovsky force are also evaluated. This force arises from asymmetric thermal emission and can alter asteroid orbits over long time scales. However, it is typically weak and accumulates gradually. For 3i Atlas, the timescale is too short and the magnitude too large for Yarkovsky effects to be significant contributors. Gravitational perturbations from undetected masses are considered briefly and dismissed. The region of space traversed by the object is well characterized. No plausible massive bodies are present that could exert the required influence without being detected independently. Internal mass redistribution is another speculative avenue. If internal structure changes such as collapse or fragmentation momentum, conservation could alter motion. However, no observational evidence of fragmentation exists. The coma morphology remains stable. Light curves do not show sudden changes indicative of breakup events. Electromagnetic interactions are sometimes proposed for charged dust or plasma environments. In interplanetary space, these forces are negligible for objects of this scale. Models confirm that such effects fall orders of magnitude below what is required. As mechanisms are evaluated, a pattern emerges. None are impossible. Several could contribute partially. But no single conventional mechanism explains the deviation cleanly without invoking parameters at the edge of plausibility. This does not imply something unknown is at work, but it does indicate that the object occupies an unusual region of parameter space. The most conservative interpretation is that 3i Atlas is an active interstellar comet with atypical composition and geometry. Its behavior may simply expand the known diversity of such objects. Interstellar origins imply formation in environments different from the solar system, where volatile inventories and structural properties may differ significantly. This interpretation remains provisional. Analysts emphasize that current models are calibrated on solar system objects. Applying them to interstellar bodies involves extrapolation. Discrepancies may reflect model limitations rather than physical anomalies. The role of this section is not to conclude but to narrow. By the end of this inward pass, the deviation has resisted explanation by straightforward application of known forces. It has not resisted explanation entirely, but it has demanded complexity. This complexity is itself informative. As data continue to accumulate, models will be refined. Parameters will be constrained. Some mechanisms may gain support while others fade. For now, the object sits at the boundary between expectation and observation, not as an outlier to be sensationalized, but as a data point forcing models to stretch. Section 7 closes with disciplined uncertainty. The deviation is real. Measurement error is insufficient to explain it. Known physical mechanisms can plausibly contribute, but do not yet provide a fully satisfying account. The object remains within physics but near its edges. The inquiry moves inward still towards synthesis, where combinations of effects and broader implications will be considered together, guided not by novelty, but by fidelity to the data that continue to accumulate as 3i Atlas moves through the inner solar system. The data now arranges itself into a shape that no one expected, and the observer sitting quietly with the glow of monitors reflected in the glass of a control room window watches as the trajectory of 3i/Atlas bends in a way that resists easy language. In classical celestial mechanics, paths are patient things. They arc and loop according to equations older than telescopes shaped by gravity, alone predictable in their long obedience to mass and distance. But here the line on the screen refuses to settle. It does not simply drift off its projected course by a fraction that can be smoothed away with error bars. It curves with intent-like regularity, not abruptly, not chaotically, but with a consistency that suggests a sustained influence acting over time. The object is not tumbling wildly, not fragmenting, not shedding material in the dramatic fashion of a comet near the sun. Instead, it adjusts. The correction is subtle, almost polite, as if the universe is whispering rather than shouting. Astronomers begin by doing what they always do. They distrust the result. They return to the raw astrometry, checking calibration stars, atmospheric distortion models, clock synchronization, pixel drift. They rerun reductions using different pipelines, different assumptions, different software written by different teams on different continents. Yet each independent path leads back to the same conclusion. The curve remains. The object is no longer following the trajectory it should. At this stage, the language remains careful. No one speaks of intelligence or design. The word intent is avoided in papers and meetings alike, replaced with phrases like non-gravitational acceleration and persistent anomalous force. These are safe words, familiar words, words that fit comfortably inside the tradition of astronomy. But privately among colleagues who have known one another for decades, the unease is audible. Non-gravitational acceleration is not rare in small bodies. Comets experience it all the time as jets of sublimating ice act like tiny thrusters. Yet 3I/Atlas does not behave like a comet. Its brightness does not vary in the way outgassing objects do. Its spectrum lacks the chemical signatures that usually betray escape in volatiles. There is no visible tail, no expanding coma, no dust plume illuminated by solar radiation pressure. If material is leaving the surface, it does so with extraordinary restraint in amounts too small to see yet somehow sufficient to alter a trajectory measurable across millions of kilometers. The observer considers the scale of this contradiction. To change course so smoothly, the force must be continuous. To remain invisible, the mechanism must be efficient beyond known natural processes. Radiation pressure is considered the gentle push of sunlight itself, but the mass and estimated surface properties of 3I/Atlas do not allow for such a response unless the object is thinner than paper, a cosmic sail drifting between stars. That hypothesis is explored, modelled, debated, and ultimately found wanting. The curvature does not match the signature of light-driven motion. Something else is at work, something that does not fit neatly into any existing category. As days pass, the curve becomes more pronounced. Not dramatic enough to alarm the public, not sudden enough to trigger headlines, but persistent enough to erode confidence in every simple explanation. The object seems to favour a particular orientation relative to its path, as if maintaining a stable attitude. This alone is unusual. Most small bodies tumble their rotation chaotic, shaped by collisions and thermal stresses accumulated over eons. Stability requires either chance alignment or active correction. Chance is invoked, of course, but chance becomes an increasingly strained companion as evidence accumulates. In quiet offices, researchers sketch free body diagrams on scrap paper, adding hypothetical forces, subtracting them, testing whether any combination of known physics can produce the observed result without introducing new contradictions. Each attempt feels like pushing a door that does not want to open. The curve remains stubborn, elegant, and wrong. It is at this moment that the story shifts, not in public announcements, but in the internal posture of the scientific community. The observer notices it in the tone of emails, in the length of video calls that run past midnight, in the way people stop saying probably and start saying if. If the force is not outgassing, if it is not radiation pressure, if it is not measurement error, then what remains is not a single answer, but a widening field of possibilities. Some are exotic, but still natural interactions with a previously unknown form of interstellar medium, or properties of matter not yet fully understood. Others sit uncomfortably at the edge of speculation where physics gives way to philosophy. No one crosses that edge publicly, yet the silence around it grows heavier. The curve has consequences. It means that predictions made weeks earlier are now slightly wrong. It means that pointing schedules for large telescopes must be updated. It means that every future observation carries an added layer of uncertainty. And uncertainty is a kind of gravity of its own, pulling attention, resources, and imagination toward a single point. The observer reflects on how small the deviation is in absolute terms. From a cosmic perspective, it is nothing, a whisper in the void. But science has always advanced by listening to whispers. Neptune was discovered because Uranus did not move exactly as expected. Mercury's orbit precessed in a way Newtonian gravity could not explain, and from that discrepancy came general relativity. Anomalies are where theories go to be tested and sometimes where they go to die. 3. I/Atlas now sits squarely in that tradition, an object whose path refuses to be obedient. The curve is not just a line on a graph. It is a question written across interstellar space. The observer feels the weight of it not as fear, but as a quiet alertness. Whatever the cause, this behavior demands attention, and attention changes the relationship between humanity and the sky. No longer is the object a distant curiosity, a visitor passing through unnoticed. It has become a participant in an ongoing conversation, one in which every new data point is a word, every recalculated ephemeris a pause. The curve continues to unfold day by day, and with it unfolds a deeper realization the universe is not obligated to conform to expectation. Sometimes it bends gently but decisively, inviting those who watch to follow the bend and see where it leads. Prediction is the quiet backbone of astronomy, an unspoken contract between mathematics and the sky, and the observer understands that this contract is now under strain. For centuries, the power of celestial science has rested not only in explaining what is seen, but in stating clearly what will be seen next. Where a planet will be months from now, when an eclipse will darken a city centuries in the future, how a newly discovered object will drift across the stars if nothing interferes. With 3 I/Atlas, that confidence begins to thin, not collapsing all at once, but fraying at the edges in a way that makes everyone uneasy. Each new positional update arrives carrying a slight disagreement with the forecast made only days earlier. The differences are small enough to be dismissed individually, yet together they form a pattern that cannot be ignored. The observer watches as prediction intervals widen, uncertainty cones stretching like shadows at dusk. This is not how interstellar objects are supposed to behave. They arrive fast, pass through, and leave again, their paths shaped almost entirely by the gravity of the sun during a brief encounter. Once their hyperbolic trajectory is measured, the future should be boringly clear. But 3 I/Atlas refuses to settle into boredom. Its future positions drift just enough to force constant recalculation, constant vigilance. Astronomers do not panic. Panic has no place here. Instead, they respond with methodical intensity. Orbit determination teams update models daily, sometimes hourly, folding in every new data point, checking residuals, adjusting parameters. The mathematics becomes heavier, more cautious, layered with assumptions explicitly stated rather than quietly implied. Yet even with this care, prediction remains slippery. The observer notes how language shifts in internal documents. Phrases like "will pass" give way to "is expected to pass," then to "appears likely to pass." Each word adds a cushion between statement and certainty. This linguistic drift mirrors the scientific one. It is not fear, but respect for a system that is no longer fully understood. One of the most unsettling aspects is the apparent smoothness of the deviation. If prediction were slipping due to chaotic behavior, sudden outbursts, or fragmentation, the models would show sharp discontinuities. They do not. Instead, the discrepancy grows steadily, as if some guiding influence remains active and stable over time. This steadiness undermines easy explanations. The observer reflects on how nature usually announces its violence. Comets flare, asteroids tumble, stars erupt. Here there is no drama, only persistence. The object behaves as though it is following a plan, though no one dares to say that word aloud. The idea of course correction arises tentatively in conversation, immediately softened with qualifiers. Correction implies intent, and intent implies agency, which is a bridge astronomy has never crossed lightly. Still, the mathematics does not care about philosophical discomfort. It describes motion faithfully, and what it describes is motion that adapts. As prediction becomes less reliable, observation grows more urgent. Telescope time, always precious, is reallocated. Instruments that had been scheduled months in advance are nudged aside to make room for another look, another spectrum, another attempt to catch whatever subtle process is at work. The observer senses a tightening of focus across the global network of observatories. This is what happens when something begins to challenge expectation. Attention converges. Different teams working independently begin to converge on the same questions. How stable is the acceleration? Does it vary with distance from the Sun? Is there any correlation with rotation phase, however faint? Each answer spawns more questions, branching outward like a fractal. Meanwhile, the slipping predictions have a practical consequence. They complicate communication beyond the scientific community. When journalists inquire about where 3I/Atlas will be weeks from now, the answers become carefully hedged. There is no deception here, only honesty about uncertainty, but the effect is noticeable. The public is accustomed to space being precise, to countdowns and trajectories plotted with unwavering confidence. Uncertainty invites curiosity, and curiosity invites speculation. The observer is aware of this background hum, the quiet growth of narratives beyond the data. Yet within the observatories the tone remains disciplined. The focus is on narrowing uncertainty, not inflaming it. One subtle shift stands out. Traditionally, prediction errors are treated as noise to be minimized. Here they are treated as signal. Each deviation is logged, analyzed, compared against theoretical expectations. The failure of prediction becomes informative. It tells a story of a system responding to something not yet named. The observer finds this inversion fascinating. The thing that undermines confidence also deepens understanding. It is a reminder that science advances not by perfect prediction, but by the careful study of its failures. As days turn into weeks, a longer-term implication emerges. If 3I/Atlas cannot be reliably predicted over short timescales, then extrapolating its past becomes equally fraught. Where did it come from exactly? What path did it follow through interstellar space before entering the Sun's domain? These questions depend on running the equations backward and backward. Prediction is even more sensitive to small uncertainties. The observer realizes that the object's history may be slipping out of reach just as its future does. This is deeply unsettling. Astronomy often prides itself on reconstructing ancient events with exquisite detail. Here, an object present and observable refuses to yield a clean narrative. The past becomes as ambiguous as the future. In response, some researchers attempt a different approach. Instead of forcing the object into existing models, they explore parameter spaces more freely, allowing for forces that vary with time in unconventional ways. These explorations are cautious, bounded by known physics, yet they stretch those bounds to their limits. The results are suggestive but inconclusive. Many models can fit the data if given enough freedom, but freedom without constraint explains nothing. The observer senses a collective hesitation. No one wants to be the first to propose an explanation that cannot be defended rigorously, and yet doing nothing is not an option. The slipping predictions continue. They are not dramatic enough to trigger alarms, but they are persistent enough to demand response. In this tension, the observer finds a familiar rhythm. Science often advances in this uncomfortable space where certainty erodes before new understanding solidifies. It is not a failure of knowledge, but a transition. 3I/Atlas. By refusing to be easily predicted forces, a re-evaluation of assumptions so deeply embedded they are rarely spoken. It asks whether motion through space can always be treated as passive, whether small bodies must always be at the mercy of larger ones. The observer does not answer these questions. No one does not yet. Instead, they continue to watch, to measure, to predict again and again, knowing each prediction will be slightly wrong, and that in those small wrongnesses lies the key to whatever truth is waiting to be uncovered. The observer now turns inward, away from prediction alone, and toward the forces that shape motion, because prediction fails only when some influence has been overlooked or misunderstood. In the outermost accounting of celestial mechanics, gravity dominates. Mass attracts, mass distance weakens the pull, and trajectories follow curves that can be drawn cleanly on paper. This framework has explained planets, comets, asteroids, and even passing interstellar visitors with remarkable success. Yet 3I/Atlas persists in moving as though gravity is not acting alone. The deviations are modest, but they are systematic, and systematic behavior demands a cause. The observer begins with the smallest recognized forces, the ones often dismissed as negligible, until precision demands attention. Radiation pressure is one such force. Light carries momentum, and when photons strike a surface, they impart a tiny push. For most objects, this push is vanishingly small compared to gravity, but over time it can accumulate measurable effects, especially on bodies with low mass or large surface area. The observer examines whether radiation pressure could account for the observed drift. Models are constructed assuming different shapes, reflectivities, and orientations. The results show that while light can nudge an object, the magnitude and direction of the acceleration seen in 3I/Atlas do not align cleanly with this explanation. Radiation pressure acts outward from the Sun, predictable in direction, yet the object's motion shows subtler variation. The force is present but insufficient. Next comes thermal emission. When an object absorbs sunlight and later re-emits that energy as heat, the delayed emission can create a gentle thrust. This is known to alter the paths of small asteroids over long periods. The observer considers whether such an effect could be unusually strong here. That would require specific conditions, a particular rotation state, uneven heating, and material properties that favor delayed re-radiation. Data are sparse, but constraints can still be applied. The calculations suggest that thermal forces could contribute, but again they struggle to match both the strength and consistency of the observed deviation. The effect should vary as the object rotates, imprinting a periodic signal. Such a signal is not clearly present. The observer notes this absence carefully. When expected variability does not appear, it becomes as informative as variability itself. Attention then shifts to outgassing, the hallmark of comets. As volatile materials warm, they sublimate, escaping as gas and dust and pushing the nucleus in the opposite direction. Outgassing can produce non-gravitational acceleration, sometimes strong enough to noticeably alter orbits. The observer asks whether 3I/Atlas could be behaving like a comet without advertising itself as one. Sensitive searches are conducted for signs of gas or dust. Spectra are examined for emission lines that would betray common volatiles. Images are stacked to look for a faint coma. The results are quiet. If outgassing is occurring, it is subtle, far below the dramatic displays seen in typical comets. This does not rule it out entirely, but it constrains it tightly. Any mass loss would have to be both low-level and remarkably steady. Such steadiness is unusual. Cometary activity often flickers, responding to sunlight and rotation. Here the acceleration appears smooth, persistent, and oddly disciplined. The observer pauses on this word not as a claim, but as a description of behavior. Disciplined motion suggests regulation, even if the regulator is purely physical. The investigation continues inward toward the object's interaction with its environment. The solar wind, a stream of charged particles flowing outward from the sun, can exert pressure and induce electromagnetic effects on bodies with conductive or magnetized materials. For most natural objects, these effects are negligible. Yet interstellar objects may carry unfamiliar compositions forged in environments unlike the solar system. The observer considers whether unusual electrical properties could amplify solar-wind interactions. Models here become speculative, not in the sense of abandoning physics, but in exploring parameter spaces rarely relevant before. The conclusion remains cautious. Even under generous assumptions, solar wind forces seem too weak to dominate. They might contribute a fraction of the observed effect, but not the whole. Each candidate force is weighed, tested, and found wanting. None can be dismissed outright, yet none stands tall enough to explain the motion alone. This accumulation of partial explanations creates a peculiar landscape. The acceleration of 3I/Atlas appears to be real, measurable, and persistent, but it resists reduction to a single known cause. The observer recognizes this pattern from other moments in science. It often signals that a system is operating at the intersection of multiple effects, each modest on its own but together significant. Alternatively, it may indicate that a familiar process is occurring in an unfamiliar regime. Both possibilities are unsettling because they erode the comfort of clear categorization. The observer reflects on how astronomy prefers clean labels. Planet, asteroid, comet, interstellar object. Each comes with an expected suite of behaviors. 3I/Atlas occupies the label of interstellar object, yet behaves as though that label is incomplete. The forces acting on it may be ordinary, but their balance is not. As analysis deepens, attention turns to the object's physical form. Shape matters profoundly. A compact sphere responds differently to forces than a thin, elongated body. Surface texture, porosity, and internal structure all influence how energy is absorbed and released. Without direct imaging, shape must be inferred indirectly through light curves and subtle changes in brightness. These data suggest variability, but not enough to pin down a definitive form. Some models favor elongation, others a more irregular structure. Each shape alters the effectiveness of radiation and thermal forces. The observer notes how sensitive the conclusions become to assumptions about geometry. This sensitivity itself is telling. It suggests that 3I/Atlas exists near a threshold where small changes in physical properties produce noticeable dynamical consequences. In such regimes, intuition often fails. The observer remains disciplined, resisting the temptation to privilege the most intriguing models over the most defensible ones. The process is slow, iterative, and often frustrating, yet there is a quiet satisfaction in watching complexity emerge honestly from data rather than imagination. As weeks pass, refinements accumulate. The combined influence of weak outgassing, thermal emission, and radiation pressure begins to approximate the observed acceleration more closely, though still imperfectly. The fit improves, but only by allowing parameters to sit near the edges of what is considered typical. This raises a subtle question. Is 3I/Atlas extreme, or are current notions of what is typical simply incomplete? The observer leans toward the latter, not out of optimism, but because history favors it. Many times before, objects once thought anomalous have expanded understanding rather than overturned it. Still, the present case carries a distinctive tension. The forces under consideration are not exotic, yet their combination yields behavior that feels almost deliberate in its consistency. The observer does not ascribe purpose. Purpose lies outside the language of physics. Instead, the focus remains on causation. Whatever the cause, it operates continuously, quietly, and with remarkable stability. This stability narrows the field. It suggests a mechanism tied intimately to the object's structure and its interaction with sunlight, not to transient events or random encounters. The observer senses that the explanation when it comes will likely be simple in principle, but subtle in execution. Such explanations often arrive late after patience has been tested. For now, the investigation continues inward toward composition and internal makeup, because forces ultimately act through matter. The motion of 3I/Atlas is a clue, not a conclusion. It points inward, inviting closer examination of what this object is made of, how it responds to energy, and why those responses manifest as motion that cannot be ignored. The observer moves further inward, away from external forces and toward the substance of the object itself, because every force leaves its signature only through the material it acts upon. Motion is not an abstract curve, but a response shaped by density, structure, and composition. If 3I/Atlas accelerates in a way that resists simple explanation, then the answer may lie not in what pushes it, but in what it is. The first consideration is density. An object with unusually low density reacts more readily to weak forces. Porous material riddled with voids behaves differently from compact rock. Light penetrates deeper, heat travels unevenly, gases migrate along hidden pathways. The observer examines the constraints that can be inferred from brightness and mass estimates. Direct mass measurement is impossible at this distance, but limits can be set. The object reflects a modest amount of sunlight, suggesting either a dark surface or one that is not especially reflective. If the mass is low relative to size, then radiation and thermal forces gain leverage. Yet even generous assumptions do not fully close the gap. Low density helps, but it does not solve everything. The investigation then considers porosity more carefully. Highly porous bodies are known in the solar system, especially among comets, formed in cold outer regions. Such bodies can trap volatile materials beneath a fragile crust. When warmed gases seep out slowly, sometimes invisibly exerting steady pressure rather than explosive jets, the observer recognizes that this scenario fits several constraints at once. It allows for outgassing without a visible coma, steady acceleration without dramatic variability, and a response that changes smoothly with solar distance. Still, porosity alone does not explain why the effect remains so consistent. Even porous comets tend to show some irregularity as different regions warm and cool. This leads inward again toward internal structure. If the object's interior is unusually uniform, lacking strong compositional gradients, then its response to heating could be correspondingly uniform. The observer considers how such uniformity might arise. Interstellar space is not kind to fragile objects. Over millions or billions of years, radiation impact and thermal cycling can erode complexity, stripping away layered structures and leaving behind something more homogeneous. 3. I/Atlas may carry the signature of long isolation, a body simplified by time. Composition becomes the next focus. Spectral observations offer limited clues, but they do indicate a surface not dominated by fresh ice. Instead, the surface appears processed, altered by exposure to cosmic radiation. Such processing can create refractory crusts sealing volatiles beneath. When heat finally penetrates these layers, release can be slow and controlled. The observer notes how this aligns with the steady acceleration observed. It also aligns with the object's interstellar origin. An object ejected from another system would have spent vast spans of time in deep cold, accumulating radiation damage and chemical alteration. Its surface would not resemble a young solar system comet. The chemistry beneath that surface could be unusual, containing ices unfamiliar in abundance or mixture. The observer remains careful. Unusual does not mean impossible. It means outside the limited sample of bodies studied so far. The inward path continues to mechanical properties. Strength matters. A body that is too weak fragments, producing obvious debris. One that is too strong resists deformation and seals in volatiles. 3. I/Atlas appears to sit between these extremes. It does not break apart, yet it may allow gradual gas escape through microfractures. Such fractures could be distributed evenly, producing a net force aligned in a stable direction relative to the Sun. The observer finds this possibility compelling, though difficult to test directly. It relies on inferences layered upon inferences, each reasonable but none decisive alone. Rotation now enters the picture. How an object spins influences how it heats and cools. Rapid rotation tends to average temperatures, smoothing out extremes. Slow rotation allows strong day and night contrasts. Light curve data hint at rotation, but the signal is weak. If rotation is rapid and stable, it would further support the idea of uniform response. The observer examines whether the direction of acceleration aligns with what would be expected from averaged heating. It appears broadly consistent, though uncertainties remain large. Here the observer feels the limits of remote sensing acutely. Without a close encounter, the object remains a silhouette against the stars, its internal life inferred only through motion. The inquiry presses deeper toward the scale of grains and pores. Thermal conductivity depends on how particles touch, how voids interrupt heat flow. A material composed of loosely bound grains conducts heat poorly, creating shallow thermal waves. Heat penetrates only a short distance before being re-emitted. This can lead to a surface that reacts quickly to sunlight while insulating the interior. If volatile materials reside just below this insulating layer, they may sublimate slowly and steadily. The observer notes how this microstructure could amplify thermal forces beyond what simple models predict. Standard assumptions often treat surfaces as continuous solids. If 3I/Atlas deviates strongly from that assumption, then standard predictions would naturally fall short. This realization shifts the tone of analysis. The problem may not be that the object is extraordinary, but that the models are overly simplified. Interstellar objects have lived different lives. Applying solar system expectations to them may be inappropriate. The observer senses a quiet recalibration underway in the community. Discussions turn less toward anomalies and more toward expanding parameter spaces. What ranges of porosity, conductivity, and composition are plausible for bodies formed around other stars? How does long-term exposure to interstellar radiation alter material properties? These questions have no immediate answers, but they frame the problem in a productive way. As composition is considered, the possibility of layered chemistry arises. Some ices sublimate at lower temperatures than others. If the object contains a mix, sublimation could occur in stages. Yet the observed acceleration does not show clear stages. This suggests either a dominant volatile or a situation where multiple processes blend smoothly. The observer remains cautious. Absence of evidence is not evidence of absence, but patterns matter. The smoothness persists as a defining feature. Another inward step considers isotropy. If gas escapes equally in all directions, there is no net thrust. To produce acceleration asymmetry is required. The observer asks where that asymmetry might originate. One possibility is a preferred orientation of pores or fractures shaped during formation or altered by long-term stress. Over time, weak structures collapse, leaving behind those aligned with stress fields. In interstellar space, such fields are minimal, but internal stresses from rotation and thermal cycling remain. The resulting structure could be subtly directional. This idea is difficult to test, yet it provides a plausible route from material properties to directional force without invoking dramatic activity. The observer appreciates how this explanation remains grounded in physics even as it stretches intuition. As the analysis reaches deeper layers, a broader implication emerges. If 3I/Atlas behaves this way because of its material nature, then other interstellar objects may do the same. The sample size is small, but each new arrival may reveal behaviors that challenge established categories. The observer does not leap to conclusions. Instead, they note that the solar system has been a biased laboratory. Its small bodies formed under similar conditions. Interstellar visitors broaden the experiment. The inward journey through matter concludes with a sense of provisional coherence. The acceleration of 3I/Atlas can be reconciled with known physics if one allows for unfamiliar combinations of density, porosity, composition, and structure. None of these require new laws, only patience and humility. Yet even as this material explanation gains strength, it does not erase the unease. The behavior remains precise, almost tuned. The observer accepts that this feeling may be psychological, a product of confronting the unfamiliar. Science demands that such feelings be acknowledged and then set aside. What matters is that motion traces back to matter, and matter carries the memory of its history. In the slow, steady drift of 3I/Atlas, the observer reads, not intent, but inheritance. The object moves as it does because of what it has been shaped long before it entered the sun's light. understanding that inheritance requires looking ever deeper toward formation and origin, where the final pieces of this puzzle may yet be found. The observer now moves further inward beyond present structure and composition toward origin, because every material property carries the imprint of formation. An object does not arrive in interstellar space by accident alone. It is shaped by a parent system, by processes that operate over immense spans of time, and by the moment of ejection that sends it wandering between stars. The peculiar motion of 3I/Atlas, when traced backward through inference rather than certainty, becomes a record of where it may have come from and how it may have been made. The first consideration is the environment of formation. Planetary systems differ widely in mass temperature gradients and chemical makeup. Around some stars, disks are rich in volatiles, while around others, heavy elements dominate. The observer reflects that the solar system is only one example among countless possibilities. Bodies formed elsewhere may possess combinations of materials rarely seen locally. If 3I/Atlas formed in a disk colder or chemically distinct from that of the Sun, its interior may contain volatiles that sublimate gently under solar heating, rather than explosively. This could explain the steady, disciplined acceleration observed. The origin environment thus becomes a key variable, not an afterthought. The observer then considers the timing of formation. Early formed bodies experience different conditions than those assembled later. In young disks, heat from the central star and from radioactive decay can alter materials profoundly. Later, formed objects may remain colder, preserving fragile compounds. If 3I/Atlas formed late in its system's history, it may retain a composition that responds smoothly to heating, lacking the sharp transitions associated with more processed bodies. This possibility aligns with the absence of dramatic activity. The inward path continues to the mechanism of ejection. To become interstellar, an object must gain enough energy to escape its parent star. This often occurs through gravitational encounters with giant planets. Such encounters can be violent, stretching and stressing the object. Weak bodies fragment. Stronger ones survive, but may be reshaped internally. The observer considers whether the uniformity inferred in 3I/Atlas could be the result of such a trial. Internal weaknesses would have been exposed, leaving behind a structure that responds coherently to stress. The ejection event itself may have acted as a filter, selecting for bodies capable of enduring long journeys. Those that survive are not representative of all small bodies but of a hardened subset. This selection bias may explain why interstellar objects appear odd when compared to typical solar system bodies. They are survivors of extreme processes. The observer then turns to the long interstellar voyage. For millions or billions of years, 3I/Atlas would have travelled through a sparse but relentless environment. Cosmic rays penetrate deeply altering chemistry and breaking molecular bonds. Micrometeoroid impacts erode surfaces slowly. Thermal cycling is minimal, but radiation damage accumulates. Over time, such processes can homogenize material properties, smoothing gradients and sealing surfaces. The observer sees how this could contribute to the object's steady response to sunlight. The interstellar medium, though thin, is persistent. Its effects are subtle but cumulative. By the time 3I/Atlas entered the solar system, it may have been profoundly altered, carrying a surface shaped less by formation than by endurance. The trajectory through interstellar space also matters. Velocity relative to the surrounding medium determines impact energies and radiation exposure. If 3I/Atlas travelled unusually fast or through particularly active regions, its surface chemistry could be further modified. The observer cannot reconstruct this journey precisely, but acknowledges that such history leaves fingerprints. These fingerprints are read indirectly through motion and response rather than direct sampling. The inward focus narrows to angular momentum and spin history. An object's rotation can be altered by asymmetric outgassing collisions or tidal interactions during ejection. Over time, rotation may settle into a stable state. If 3I/Atlas achieved such stability early, its later evolution would be governed by averaged effects rather than chaotic ones. This would again support the smooth acceleration observed. The observer notes how many independent threads converge on stability as a central theme: stability of structure, stability of rotation, stability of response. None of this implies design. It implies survival. The objects that endure are those that find stable configurations. As origin is considered, the observer also reflects on population statistics. Interstellar objects are rare visitors, but they are not rare overall. Countless bodies are ejected from planetary systems during formation and evolution. The ones detected are those that pass close enough to the Sun and reflect enough light to be seen. This detection bias favours certain sizes, compositions and behaviours. 3I/Atlas may represent not an anomaly, but a visible member of a much larger unseen population. Its behaviour may be common among interstellar travellers, even if it appears unusual from a solar system perspective. This realization shifts the narrative subtly. The question becomes not why this object behaves as it does, but why expectations were narrower to begin with. The observer senses that astronomy is being gently reminded of its limited sample size. The inward journey continues toward chemical pathways. Formation in another system may allow the incorporation of compounds rare here. Some ices sublimate over a narrow temperature range, producing sudden activity. Others transition more gradually. If 3I/Atlas contains a mix favouring gradual release, its acceleration would appear smooth. The observer considers laboratory studies of such materials, noting how small differences in composition yield large differences in behaviour. These studies provide a bridge between abstract models and physical reality. They suggest that the observed motion need not be exotic. It may simply reflect chemistry unfamiliar to local experience. As the focus tightens, the observer confronts uncertainty directly. Origin cannot be observed, only inferred. Each inference carries assumptions. The observer maintains discipline, separating what is constrained from what is merely plausible. It is constrained that 3I/Atlas is interstellar, that its trajectory is hyperbolic, that its motion shows non-gravitational acceleration. It is plausible that this acceleration arises from material properties shaped by formation ejection and interstellar travel. Beyond that, certainty fades. This fading is not failure. It marks the boundary of current knowledge. The observer recognizes that future interstellar visitors will sharpen this picture. Patterns will emerge only with numbers. For now, each object is a case study, rich but incomplete. The inward exploration of origin concludes with a broader understanding. The path of 3I/Atlas is not just a line through space, but a narrative compressed into motion. Its deviations from prediction are echoes of distant environments and ancient events. The observer does not seek meaning in this narrative, only mechanism. The object moves as it does because of where it formed, how it was shaped, and what it endured. The solar system encounter is brief, a moment of illumination in a journey measured in cosmic time. Understanding that journey requires humility and patience, qualities as essential to astronomy as mathematics. As the observer prepares to move further inward, still toward the smallest scales of process and interaction, the sense grows that 3I/Atlas is not challenging physics, but expanding its context. The laws remain intact. The stage on which they act has simply grown larger. The observer moves inward again past origin and history toward the smallest active scales that still influence motion, because even the most subtle drift arises from countless microscopic interactions. At this level, forces are no longer described only in terms of trajectories and masses, but in exchanges of energy among grains, molecules, and defects too small to be seen directly. For 3I/Atlas, whose large-scale behaviour appears smooth and persistent, the explanation may lie in the quiet coordination of processes operating far below the threshold of direct observation. The observer begins with surface physics. Sunlight arriving at the object does not strike a uniform plane. It encounters a landscape of grains, cracks, and cavities, each with its own orientation and thermal response. Photons are absorbed, scattered, or reflected, and their energy is redistributed unevenly. At the microscopic level, this creates gradients that do not average out perfectly even when rotation is rapid. Heat flows along contact points between grains across voids filled with tenuous gas and through amorphous solids altered by radiation. The observer considers how these pathways differ from the idealized surfaces often assumed in models. Real surfaces are messy, and messiness can produce emergent order. When energy transport is inefficient, small temperature differences persist. These differences drive slow processes such as sublimation of trapped volatiles and thermal creep, where gas migrates along temperature gradients. Individually, these effects are tiny. Collectively, across billions of grains, they can sum to a measurable force. The observer reflects on how easily such contributions are overlooked, not because they are unknown, but because they are difficult to quantify. Next, attention turns to phase transitions. Many materials undergo changes in structure or state over narrow temperature ranges. In porous bodies, these transitions can occur repeatedly as sunlight cycles. For example, amorphous ice can reorganize into a more ordered form, releasing energy and freeing trapped gases. This process is slow and distributed, not explosive. The observer notes that such transitions could provide a steady source of gas without obvious outbursts. The resulting thrust would be weak but continuous, matching the observed acceleration. Importantly, the rate of this process depends more on internal structure than on surface appearance, which explains why external observations reveal little. The inward journey continues to chemistry. Radiation over long interstellar journeys alters molecular bonds, producing complex mixtures of organics and refractory residues. These materials can trap gases efficiently and release them only under sustained heating. Laboratory studies show that such irradiated ices behave differently from pristine ones, responding gradually rather than abruptly. The observer recognizes that 3I/Atlas likely carries such processed material. Its chemistry is not exotic in principle, but unfamiliar in practice. The solar system offers few direct analogues. This unfamiliarity complicates interpretation, but it also opens a pathway to explanation that does not require extraordinary assumptions. The observer then considers electrostatic effects. As sunlight and solar wind interact with the surface, charges can build up, especially on insulating materials. On small scales, these charges influence how dust grains adhere or repel each other. In extreme cases, electrostatic lofting can move particles across a surface. While such effects are subtle, they can alter surface texture over time, changing how heat is absorbed and emitted. The observer does not suggest that electrostatics drive the acceleration directly, but that they may shape the surface in ways that enhance other processes. The microphysics of charge, heat, and material strength intertwine. None dominates alone. Together they create conditions for persistent low-level thrust. As the focus narrows further, the observer reflects on scale coupling. Microprocesses matter only when their effects align across larger scales. Random activity cancels out. Directional activity accumulates. For 3I/Atlas, the smoothness of the acceleration suggests alignment. This alignment may arise from geometry. If the object has a preferred orientation relative to the Sun, even weak processes can produce a net effect. The observer considers whether such orientation could be maintained passively without active control. Stable rotation states exist determined by shape and mass distribution. Once established, they can persist for long periods. In such a state, the same regions receive sunlight in the same way, reinforcing consistent behavior. The observer notes how this provides a bridge between microphysics and macroscopic motion. Tiny processes acting consistently in the same regions yield a steady force. Another microprocess comes into view: gas diffusion through porous media. When gas molecules are released below the surface, they do not escape freely. They collide with pore walls, exchanging momentum. This interaction produces a pressure gradient that can exert force on the solid framework. The direction of net force depends on the geometry of pores and the temperature gradient. In materials with aligned pore structures, diffusion can be anisotropic, favoring certain directions. The observer finds this possibility intriguing. It offers a mechanism for directional thrust without visible jets. The process is slow, steady, and difficult to detect remotely. It fits the data not by dramatic signature but by quiet consistency. The inward exploration continues to defects and fractures. Even in apparently uniform materials, microscopic cracks concentrate stress and heat. These cracks can act as conduits for gas and as sites for chemical change. Over time they may evolve, but if the overall stress environment is stable, their distribution remains roughly constant. The observer considers how such stability could persist through interstellar travel. The absence of strong tidal forces and collisions allows fragile structures to survive. By the time the object enters the solar system, its microstructure may be frozen in responding predictably to the new energy source of sunlight. The observer acknowledges the difficulty of proving any of this directly. The data available are limited and each inference rests on layers of modeling. Yet the convergence of multiple microprocesses toward the same qualitative behavior lends confidence. The acceleration of 3I/Atlas need not arise from a single dominant mechanism. It may be the emergent result of many small ones, each operating at the edge of detectability. This realization shifts emphasis away from searching for a singular cause and toward understanding how complex materials behave under simple conditions. The observer recognizes a familiar pattern. In many areas of physics, macroscopic order emerges from microscopic complexity. Here that order takes the form of a smooth deviation from prediction. It is not mysterious, only intricate. The inward focus now approaches the limits of relevance. Below a certain scale, processes average out, completely leaving no net effect. The observer remains attentive to where that boundary lies. The fact that an effect is observed at all implies that the averaging is incomplete. Something preserves asymmetry. Geometry, rotation, and material anisotropy likely play this role together. The observer resists the temptation to assign narrative significance to this coordination. It is enough to note that physics allows it. As the microphysical picture solidifies, a subtle shift occurs in how the object is perceived. It no longer appears as a point mass with odd motion, but as a complex system whose internal processes reach outward into space through motion. The observer finds this perspective grounding. It replaces unease with curiosity. The behavior of 3I/Atlas does not challenge known laws. It challenges assumptions about simplicity. The inward journey through microprocesses ends with a sense of provisional completeness. The pieces fit, though gaps remain. Future observations may refine or revise this picture, but the current understanding suffices to explain why prediction falters. Prediction assumes smooth inputs and known responses. 3I/Atlas provides smooth outputs arising from poorly constrained inputs. The discrepancy lies not in the object but in the limits of observation. With this realization, the observer prepares to move inward one final step toward interpretation, at the boundary between explanation and restraint, where science must decide not only what can be said but how cautiously it should be said. The observer now approaches the innermost boundary that still belongs to explanation rather than conclusion, a region defined less by physical scale than by methodological restraint. At this point, most outward layers have been examined. Forces have been considered and material properties, explored origins traced and microprocesses assembled into a coherent framework. What remains is not another mechanism, but the discipline of deciding how far interpretation may go without exceeding evidence. In astronomy, this boundary is essential. It is where curiosity meets caution, and where language itself becomes a tool that must be handled carefully. The observer recognizes that 3I/Atlas sits precisely at such a boundary. Its behavior is sufficiently unusual to invite strong narratives, yet sufficiently explicable to resist them. The task here is not to resolve mystery, but to prevent it from being manufactured. The observer reflects on how scientific explanations often harden prematurely shaped by the desire for closure rather than the weight of data. In this case, closure would be misleading. The acceleration of 3I/Atlas can be explained plausibly through combinations of known processes, but none of these explanations can be isolated, confirmed, or ranked definitively. The responsible stance is therefore plural, not singular. Multiple mechanisms remain in play, each constrained, none privileged beyond evidence. This plurality is not weakness, it is accuracy. The observer considers how prediction failure has altered expectations. Earlier sections showed how slipping trajectories undermined confidence, not because laws failed, but because inputs were incomplete. Here that lesson deepens. The observer understands that explanation itself must remain probabilistic. Any statement about what 3I/Atlas is doing must carry an implicit margin of uncertainty, not as a disclaimer, but as an integral part of meaning. This demands a particular tone. Words like appears consistent with and constrained by are not hedges. They are measurements of epistemic distance. The observer notes how easily this discipline can be misread outside scientific contexts. To some, uncertainty implies ignorance. To others, it invites speculation. Within science, uncertainty is simply resolution stated honestly. The observer remains anchored in this internal logic. Attention turns briefly to the social dynamics of interpretation. As data circulate, different research groups emphasize different aspects. Some focus on material properties, others on dynamical modeling, others on population statistics. Each emphasis produces a slightly different narrative, even when based on the same facts. The observer does not see this as fragmentation, but as parallel exploration, Over time, convergence may occur, but it cannot be forced. The temptation to declare one explanation correct before convergence emerges is strong, especially when public attention grows. The observer resists this temptation. The role is not to satisfy curiosity, but to align statements with evidence. At this inner boundary, the observer also confronts language that edges toward agency. Phrases like adjustment response or regulation appear naturally when describing smooth, persistent behavior. These words are descriptive shortcuts, not claims of intent. Yet they carry connotations that extend beyond physics. The observer is acutely aware of this semantic risk. Care is taken to anchor every such term in physical process. Adjustment refers to equilibrium. Response refers to interaction. Regulation refers to feedback loops inherent in material behavior. None imply awareness or purpose. The observer maintains this clarity not only for correctness, but to preserve the integrity of the explanatory framework. Science loses coherence when metaphor is mistaken for mechanism. The observer then considers what is not said. There is no appeal to unknown forces, no invocation of new physics, no suggestion that current laws are inadequate. This restraint is deliberate. Extraordinary claims require extraordinary evidence, and no such evidence exists here. The behavior of 3I/Atlas fits within known physical principles, even if those principles must be applied in unfamiliar combinations. The observer recognizes that resisting novelty can be as important as embracing it. Progress often comes from extending existing frameworks rather than replacing them. The inward focus sharpens on the distinction between anomaly and outlier. An anomaly challenges a theory. An outlier expands its domain. The observer places 3I/Atlas firmly in the second category. It does not contradict gravitational dynamics or thermodynamics. It reveals a region of parameter space that has been sparsely sampled. This distinction matters deeply. Treating outliers as anomalies leads to unnecessary theoretical upheaval. Treating anomalies as outliers leads to stagnation. The observer sees that correct classification depends not on excitement, but on careful comparison with established behavior. Here, the comparison favors continuity. The observer reflects on historical parallels. Many times objects initially described as puzzling were later understood as natural consequences of broader conditions. The process is rarely dramatic. It involves years of incremental clarification. The observer senses that 3I/Atlas is at an early stage of such a process. Its current role is not to redefine physics, but to remind observers of the diversity of physical realization. The solar system has been a narrow training ground. Interstellar objects expand that training. At this boundary, the observer also acknowledges limits that may never be crossed. Some properties of 3I/Atlas may remain permanently uncertain. Without in situ measurement, density, composition, and internal structure will remain inferred rather than known. This is not a flaw of analysis, but a consequence of distance. Astronomy often works at such remove. The observer accepts that explanation does not require omniscience. It requires coherence and constraint. The present framework satisfies both. The observer turns inward one last time toward the role of the observer themselves. Observation is not passive. Choices about what to measure, how often, and with which instruments shape understanding. In the case of 3I/Atlas, increased attention has already refined models significantly. Yet the observer remains aware that attention itself can bias interpretation, amplifying perceived significance. This awareness acts as a corrective. The object is studied intensely not because it is assumed extraordinary, but because it is informative. The distinction is subtle but crucial. Informative objects deserve scrutiny without narrative inflation. As section 14 draws toward its close, the observer stands at a threshold. Beyond this point lies not deeper mechanism but synthesis. The remaining task is to integrate what has been learned into a calm, stable understanding that neither exaggerates nor dismisses. The observer feels no urgency to rush this integration. Time remains. The object will pass, data will accumulate, and understanding will mature slowly. For now, restraint is itself an achievement. It preserves the clarity of what is known, the openness of what is uncertain, and the integrity of the scientific process. The observer holds these elements in balance, preparing to move inward one final time, not toward explanation, but toward closure of description, where observation yields to quiet continuity, and the story of motion is allowed to settle without resolution imposed upon it. The observer now reaches the innermost region of the exploration, not a physical interior, but a temporal one, where the focus shifts from causes to continuation. Here the question is no longer what drives the motion of 3I/Atlas, but how that motion fits into the broader ongoing behavior of the universe once attention begins to recede. Every astronomical encounter is temporary. Objects pass through fields of view, through regions of heightened scrutiny, and then move on, carrying with them whatever remains unknown. The observer understands that this passing is not a failure of investigation, but its natural boundary. Knowledge does not require permanence of access. It requires coherence while access lasts. As 3I/Atlas continues along its path, its distance from the Sun increases, and the forces that revealed its subtle acceleration weaken. Thermal effects diminish. Any low-level release of gas slows. Radiation pressure decreases. Gradually, the object's motion settles back toward the simplicity expected of a body moving through open space. The observer notes this transition carefully. It is not abrupt. It unfolds smoothly, mirroring the steadiness that characterized the encounter itself. This symmetry reinforces the emerging understanding. The same processes that produce deviation near the Sun fade predictably as conditions change. Nothing remains unresolved in principle, even if details remain unmeasured. Prediction regains strength as forces simplify. Trajectory estimates tighten. Uncertainty cones narrow. The mathematics returns to familiar ground. The observer experiences no disappointment in this return. It signals that the system behaves consistently across regimes. Consistency is the quiet hallmark of physical law. Attention now turns to what remains after the encounter. Data collected during the passage are archived, shared, and reanalyzed. Some questions persist, but they no longer demand immediate answers. They become reference points for future discoveries. When the next interstellar object appears, comparisons will be drawn. Similarities will be noted, differences highlighted. Patterns may emerge slowly across decades rather than weeks. The observer understands that this is how understanding accumulates in astronomy. Single cases rarely decide anything. They prepare the ground. The observer reflects on how the narrative around 3I/Atlas has evolved. Initial detection framed it as a point of motion against the stars. Subsequent observation revealed deviation. Analysis unpacked forces, materials, origins, and microprocesses. At each stage, the object remained the same, yet understanding deepened. This layered growth of knowledge did not require dramatic revelation. It required patience. The observer recognizes patience as a methodological virtue as important as precision. Without patience, deviation would be overinterpreted. With patience, it becomes informative. As the object recedes, the observer resists the urge to assign final significance. There is no need to declare what 3I/Atlas ultimately represents. It is sufficient to state what has been learned. The object demonstrated that interstellar bodies can exhibit smooth, persistent non-gravitational acceleration without visible activity. It demonstrated that such behavior can be explained plausibly through known physical processes acting in unfamiliar combinations. It demonstrated that prediction, while powerful, depends critically on assumptions about material properties. These demonstrations stand on their own. They do not require embellishment. The observer also notes what has not changed. The laws governing motion remain intact. Gravity remains dominant at large scales. Energy conservation holds. Thermodynamic behavior remains consistent. The encounter did not destabilize existing frameworks. It enriched them. This distinction matters. Science progresses most reliably when new observations extend the range of application rather than overturn foundations. 3I/Atlas serves as an extension. The observer turns briefly to the human dimension not as psychology, but as practice. Teams disband from their heightened coordination. Telescope schedules normalize. Alerts quiet. Yet the experience leaves traces. Future detections will be approached with slightly altered expectations. Models will include broader parameter ranges. Assumptions about uniformity and activity will be relaxed. These changes are subtle, but they persist. The observer recognizes this as the true legacy of the encounter. Not answers, but preparedness. The inward focus narrows further toward the idea of continuity itself. Interstellar space is filled with objects like 3I/Atlas most unseen. They move steadily, shaped by their histories, indifferent to observation. Occasionally one passes close enough to be noticed. Observation then intersects briefly with an ongoing trajectory. That intersection does not define the object. It defines the observer's opportunity. The observer finds this perspective stabilizing. It places the encounter within a vast context where no single object bears disproportionate weight. As distance grows, the object's light fades. Measurements become less precise. Eventually, observation ceases. At that point, prediction carries the remainder of the journey, projecting motion outward into the dark. The observer trusts this projection not because it is perfect, but because its limits are known. Uncertainty expands with time as it always does. This expansion is not alarming. It is expected. The observer does not follow the object further, not because interest ends, but because relevance does. Attention shifts elsewhere as it must. New data streams arrive, new questions form, the cycle continues. The observer reflects on how restraint practiced throughout the investigation finds its final expression here. The temptation to conclude is strong, but conclusion would imply closure that does not exist. Instead, the observer allows the narrative to remain open-ended not as mystery but as continuity. 3I/Atlas does not resolve into a lesson or a symbol. It remains an object in motion, briefly illuminated, now receding. This acceptance marks the end of analysis. Nothing further is required. The observer has traced the path from outer motion to inner process, from detection to understanding, and finally to release. The object departs with its trajectory intact, carrying with it the quiet assurance that the universe remains consistent even when it surprises. In this final inward moment, the observer rests in that assurance. Motion continues. Space remains vast. Understanding grows incrementally. There is no need to follow further. The sky turns slowly and the work of observation moves on.